Welcome to my YouTube channel. Watch, like, share and comment. Welcome to today's lesson. My name is Mwalimu Sam Nyamo. In our today's lesson, we shall be looking at the chemical families and more specifically the alkali metals. Alkali metals, remember, are metals belonging to group 1 of the periodic table. The objectives of the lesson is that by the end of the lesson you should be able to state and describe the physical properties of alkali metals, the chemical properties of alkali metals, and the uses of the alkali metals. So we begin with the physical properties, and like you are able to see from the diagram, the atomic size of alkali metals increase down the group. That means that potassium, among the 3 elements, that is the first 20 elements, for the alkali metals, potassium has the largest atomic size. This is followed by sodium, and finally lithium has the least atomic size. Why do we have potassium having a large atomic size while lithium having the least atomic size? This is because the atomic size increases down the group. And how is it possible that the size increases down the group? Let us consider the electron configuration of these 3 elements. Lithium, for example, has an electron configuration of 2:1. That means that it only has 2 energy levels. The first occupied energy level has a maximum of 2 electrons, and then the second energy level has only 1 electron. If we were to draw the electron configuration of lithium, it would appear like this. Lithium, the first energy level with 2 electrons. Then we have the second energy level with just 1 electron. You note that we only have 2 energy levels, occupied energy levels. So let's consider sodium. Sodium, on the other hand, it has an atomic number. The atomic number is 11. That means that the electron configuration of sodium is 2:8:1. If we were to draw the electron configuration, if we were to draw now the atomic structure of sodium from this, it would mean that we would draw it like this. So we have sodium, then we have the first energy level with 2 electrons, followed by the second energy level with 8 electrons, and then we have the last occupied energy level for sodium with only 1 electron. So if you compare the 2 atoms, lithium has 2 occupied energy levels while sodium has 3 occupied energy levels. For that reason, the size of sodium is bigger than that one of lithium. If we draw the atomic structure of potassium, it should appear like this. So we have the electron configuration of potassium as follows: 2, 8, 8, 1. So it has a total of 1, 2, 3, 4 energy levels. And therefore, that one gives us an atomic structure that looks as follows. We have potassium, then we have the first energy level with 2 electrons, then we have the second energy level with 8 electrons, and finally those are 8 electrons. Then we have the third energy level again with 8 electrons, and then finally we have the fourth energy level with only a single electron. Comparing now the size of potassium here, and the size of this potassium and the size of this sodium, it is clear that the size of potassium is bigger than that one of sodium. The difference or the increase in the size of the atoms can be explained by the increase in the energy levels down the group. We look at the melting point. Lithium has the highest melting point and boiling point. That is followed by sodium, and then finally potassium as comparatively least melting point. The melting point can be explained by the fact that lithium has a smaller size. Therefore, its atoms are able to pack more closely to each other compared to potassium and sodium. And for that reason, it results to lithium having a higher melting point, and that one goes down to sodium having a least melting point, and finally potassium among the 3 members now will have the least of all the melting points. When we compare the 3 atoms by their electrical conductivity, their ability to conduct electric current, it is found that the 3 of them conduct electric current by the same rate. Why? Let us look at the electron configuration of lithium. Electron configuration of lithium is 2 to 1. That of sodium is 2, 8, 1. And then that one of potassium is 2, 8, 8, 1. Remember that the electrical conductivity is always dependent on the number of electrons that are available for electrical conductivity. In this case, any given atom uses the electrons in the outermost energy level to conduct electric current. Among our 3 members here, all of these members have a single electron in their outermost energy level. Now, this electron being the one that is responsible for electrical conductivity means that the three elements will conduct electrical conductivity by the same rate from the fact that all of them have one electron available for electrical conductivity. Finally, the ionization energy. When we speak about ionization energy, we want to look at the energy that is required to remove an electron from the outermost energy level in gaseous state. I will still refer to my electron configurations. And like you can see, we have potassium having its one electron very far from the center or very far from the nucleus, because remember that the electrons are usually attracted towards the center of the atom by the nuclear charge. So having potassium having a very big size means that its electron is held weakly as compared to the electron of sodium and the electron of lithium. For that reason, it is easier for potassium to lose an electron as compared to sodium, and the same way it is easier for sodium to lose an electron than lithium. By that, we can conclude that the ionization energy increases as we move, or decreases as we move down the group. Next, let us look at the chemical properties. How do alkali metals react with water? Before we begin, remember that their name is derived from the fact that when dissolved in water, alkali metals give a solution that is a strong alkaline. Being strong alkaline gives them the name alkali metals. Therefore, an example, sodium, which is a solid, will react with water, which is a liquid, to give us sodium hydroxide, which is aqueous, plus hydrogen gas. We check whether the reaction is balanced. On this side we have one sodium. On the product side we also have one sodium. We have 2 hydrogen atoms on the reactant side, and we have 3 on the product side. So we can try to balance the equation by having a 2 there and another 2 here, and another 2 here, so that now we have 2 sodium, we have 4 hydrogen, these are 4 hydrogen, and these ones are also 4, and then we have 2 oxygen on both sides. The reaction is balanced. Remember that all these elements react the same, only that we have potassium being more reactive than sodium and sodium being more reactive than lithium. As a matter of fact, reaction between potassium and water is very explosive and results to actually a flame. When we compare sodium, reaction of sodium with water, the reaction is vigorous and sodium darts on the surface of the water when we introduce a small size, actually the grain size, the rice grain size of potassium or of sodium into water. It darts on the surface and melts into a silvery ball The reason as to why it darts on the surface, of course, it's because it is less dense than water, therefore it does not sink. Number two, there is an hissing sound that is heard. The hissing sound is as a result of the hydrogen gas that is being produced. And then, finally, we have the sodium metal itself melting into a silvery ball. It melts because the reaction is very explosive. So if we are told to write the equation for lithium with water, we just take, we have lithium, which is a solid, reacting with water, which is a liquid, to give us lithium hydroxide, which is aqueous plus hydrogen gas. The same case, we are going to write the equation for now potassium. We can first balance. The equation is just balanced like we balanced the other one, just like that, it's balanced. We are now to write the equation for potassium with water. There you just need to change where we have lithium and just replace with potassium. And we will have now potassium plus water giving us potassium hydroxide plus hydrogen gas. So that is all for the reaction with water. We look at how the solids or the metals react with oxygen. The product formed when metals react with oxygen is metal plus oxygen gas. We always form a metal oxide. So in our case, we have sodium as an example reacting with oxygen gas will give us sodium, write it better, will give us sodium oxide. And the formula of sodium oxide is like that, and the product is solid. We balance the equation, maybe having a 2 here and another 2 there. However, this product is only when sodium reacts with limited oxygen. If you react sodium with an enriched air, that means that we have excess of oxygen, the product that is formed is not sodium oxide. We actually form sodium peroxide. And this is the formula for the peroxide. The formula for the peroxide is as follows. We have sodium solid reacting with oxygen gas to give us sodium, and this is the formula of the peroxide, which is obviously a solid. This equation is balanced by having a 2 here, and by just that we have the equation balanced. Reaction between potassium and oxygen, we just need to change what we have in the place of sodium. So reacting potassium with oxygen, this is the product that is formed it is obvious that now we will have potassium solid reacting with oxygen, which is a gas, to give us potassium oxide. Yes, potassium oxide, and this is a solid. The equation is balanced by having a 2 there. So the next thing that you might need now to know is the product that is formed when lithium reacts with potassium. When you get to this, I request that you pause the video and you try to write the equation for the reaction between lithium and oxygen. Are you back? It is this simple. You just need to replace the K for potassium with lithium. Just like that. And now you have lithium oxide as the product that is formed. Reaction with chlorine. There is no much difference between how oxygen reacts with alkali metals and the way the same alkali metals react with chlorine. The rate of reaction is also the same. That is to mean that potassium will react more, or the rate of the reaction is higher with potassium as compared with sodium, and with sodium it is obviously higher when compared with lithium. So we write the equation for the reaction between lithium with chlorine. We will have lithium as a solid reacted with chlorine, and remember it is a diatomic molecule, so we will have diatomic gas, so we will have Cl2. Then the product that is formed is lithium chloride, which is now a solid. How do you balance the equation? You balance the equation by having a 2 there and a 2 here, and the equation is now balanced. How do you write the equation for the reaction between sodium and chlorine? Very simple. You just need to replace the lithium that we have here with sodium. You just take sodium, and here you just have sodium. How do you write it with potassium? You do the same. You replace sodium with potassium, and don't forget to balance the equation. And that's all for the chemical properties of the alkali earth metals. Next, we look at the uses of alkali metals, and use number 1, the alkali metals. Sodium as a member in its pure form produces a vapor that is used to produce a yellow glow in streets. Everyone has used sodium chloride as a salt, and therefore we can say that sodium chloride is used as a food additive. We have sodium cyanide, which is used in extraction of gold. Then we have lithium compound, are used in the manufacture of dry cells. I am sure that every one of you is using either a laptop or a phone or a watch at any given point you have ever used any of those, the material that is used to make the battery that makes the watch run, powers the watch, powers the laptop, powers a smartphone, is usually made of lithium. Also, lithium oxide is widely used as a cleaning agent for processing of silica. And finally, lithium compounds are used to produce red fireworks. Having mentioned that, there are more uses of alkali metals. You can research on more. Next, we shall be looking at the alkaline earth metals, and definitely not on this class, so I advise that you watch the next clip so that you don't miss on alkali metals. Thank you for watching. Subscribe to the channel and share the video with your friends so that together we build an ocean of chemistry.